stemming from physical chemistry quantum course.
Awesome, thank you, Dimitri. All right, so my experiment was look at catalytic decomposition of chlorite from a particular enzyme. I just picked chloride dismutase, but really looking at that bond distance and how the rates were affected by a catalyst. Okay, so in the chemical reaction, we obviously used chlorite, and with chlorite, we used chloride dismutase as our enzyme, which developed molecular oxygen and chloride. Chloride dismutase contains a prosthetic group known as heme. Heme contains a metal ion called iron, and this iron is what drives the catalytic reaction forward by binding to the oxygens of the chloride. This particular reaction is pretty rare in many biological systems in that it doesn't happen very often. Most often occurs with bacteria, respirating bacteria, where they breathe in chlorite and they expel molecular oxygen and chloride ion. But currently, right now, there's not very many relationships with chloride dismutase and other heme-containing proteins. So with my structures, the first structure here is the chloride dismutase as itself. There are 5 different domains of biological structures with numerous alpha helices, amino acid side chains. Then the structure right next to it is the heme group as well. What's most notable is the iron in the middle, and this iron is in an oxidation state of +2. In the reaction we'll see later, it'll go to +3 once it binds to the oxygen, and then it'll go back to +2. This is more of a top view of the heme. Both above and below it are 2 amino acid side chains that do affect the states at which heme reacts. That's kind of a later topic in biochemistry. And then in the bottom here is just chlorite as a structure, just as a reference. Okay, so here's my catalyst mechanism. In the first step of the reaction, we have our chlorite and our heme group, and essentially we looked at how the initial momentum affected the chlorite approaching the heme, which would bind to the iron, making it go to an iron 3 state, and then eventually the chlorite would dissociate into hypochlorite, and this hypochlorite would eventually move far away, creating that interatomic distance, which is analyzed in this chapter. And then eventually it would come back, bind again with oxygen on that heme, and then dissociate completely into molecular oxygen and chloride. All right. And so this is kind of a look at the reaction itself. This is provided by Braden. And so what kind of happens is the oxygen binds to the iron, which is that orange, and then it dissociates later, and then this floating off in the distance is the hypochlorite. And the rest of the reaction would pursue as normal in the mechanism. So the method we did this was by almost any other method. We did a wave packet propagation in MATLAB, which then evolved by the time evolution operator, and we obtained time-dependent potential data by looking at the cross-sectional areas of the reaction and taking the integration values of those for probability. And then continuing on, we found the rate by using those reaction probability distributions to eventually get into our Arrhenius equation, which showed us the activation energy developed in this reaction. And so this is the wave packet simulation as itself. The red and blue simulates the reactants, and then the green here is the kind of the energy barriers itself. So this is this first peak here is the first energy barrier, and then this is the second peak. And so what we'll find out is as it proceeds, it's kind of fast, but what happens is as it approaches the energy barrier, some product will be formed. So some will surpass the energy barrier, and then some will stay back and then continue on. What was most notable was when we did low values of initial momentum, not a lot of the reactant surpassed the activation barrier, but more so what happened was quantum tunneling happened, and that some of the product was created, but very, very small amounts. But so again, as we get higher initial momentum values, more product was created and surpassed that energy barrier. And so here's kind of the data representing this. So this is just a sample of the potential data I was provided by Braden. So we have the potential energy and the distances of each molecular bond or interatomic distance. And what was noticeable was that the potential energy didn't change much at all, really. It kind of stayed the same even as we got into higher values or as time progressed. But what was most notable was the distances, the interatomic distances of the chlorite did increase as time proceeded. And that was just by the reaction itself here in these diagrams where we have our initial step and then the hypochlorite dissociates off and the distance increases as time proceeds. And then this graph again just represents that as time proceeds on, distances increase further and further. And so moving from that, when we applied the wave packet to this, here we have it when the reaction doesn't surpass the energy barrier and is more suppressed. And then here we have enough initial momentum to surpass it and we create a product. And by this diagram, we see it moving off that since there's more of a scattering here, we have more. This is a product here. And then here we just stay as a reactant. Mm-hmm. And so how this affected our temperature and rates? Well, obviously, when we increased our initial momentum, our temperature increased as well as the rate of reaction, but the activation energy did remain constant since the potentials did not change very much at all. So really, we were looking at that transfer rate as we increased our initial momentum and how the distance between the hypochlorite and the heme increased as well. And so in this diagram is our activation energy barrier. And then this is the reaction proceeding forward. And then these are just small potential energies across the reaction itself. And so with my graphs here, the effects of temperature on rate, oops, my bad. There was kind of a linear progression with temperature and rate. So as our temperature increased, the rate of reaction also increased kind of linearly. This is our rate constant more so. And then with our Arrhenius plot, there was a nice solid regression line down the middle, which kind of showed a constant activation energy by calculation. And then with our probability distribution, this is what this looked like. The orange line here is our product, and the blue line here is our reactant. So as time proceeds, less of our product, or less of our reactant is formed or is staying, and more of our product is formed, or the more likelihood of it forming. And then these two graphs are just two different showings of addition values of initial momentum. So the top one is a lower value, and so we see there is less scattering on top, which means there was less product, whereas here there is more scattering and there's more product formed. So basically what happened was my hypothesis of seeing the activation energy of potentials correlate was how I expected, where the activation energy remained the same, and really what increased was the transfer rate and the distance between hypochlorite. And then also what was unique was the quantum tunneling that did appear. But for future works, I'd like to see this be more reconfigured, maybe develop some wells so we can analyze the potential energy more effectively, or just use wells to establish and see what happened there. With that, I will take any questions.
Okay, well, thank you. Anyone wanted to learn more about enzymes or challenge Bill with questions?
So your Arrhenius plot, when you do linearization, is it proper to add the highest energy or the lowest X value?
In this case, probably not. I did that more so just to see two different extremes and what was happening in the reaction.
Okay, because like the lower temperature was very linear, and then it like.
And then there was
jumped
one up. Yes, that was just from as kind of an experiment to see what would happen at the extremes.
So then your like R squared value would get better if you exclude that.
Yes.
More questions? One. More questions? Two. More questions? Three. Let's thank Bill once again.